The work of Nobel Prize has transformed our understanding of the world. While approaching the Nobel Prize winners in chemistry, we not only learn their achievements, but also the spirit of honesty, tenacity, innovation, and forging ahead. Hello everyone, welcome to today's class, Approaching Nobel Prize Winner in Chemistry. 同学们大家好，欢迎走进今天的课堂，走进诺贝尔化学奖。Today I will introduce to you a famous scientist whose name is Gerhard Ertl for the reaction at solid surfaces. In our daily life, we may have become used to some of the phenomena we see and think they deserve to be so. But have we ever thought why? For example, after rain, we can see that the small droplets on the leaves are nearly spherical. After accidentally breaking the thermometers, the mercury droplets dropped to the ground, and the mercury droplets were spherical. Gas or liquid molecules can be absorbed on solid faces, and these phenomena are related to the surface. In today's class, I will introduce you a scientist, Gerhard Ertl, who has studied the surface of matter for decades. Gerhard Ertl is a German scientist. He won the Nobel Prize in Chemistry in 2007 for his studies of chemical process on solid surfaces.
Royal Highnesses, ladies and gentlemen. The famous physicist Werner Heisenberg begins his autobiography with the sentence, Wissenschaft wird von Menschen gemacht. That means science is made by man. And since you honor me not for a singular discovery, but for a lifelong attempt to understand how chemical reactions at solid surfaces proceed, then it's obvious that also many people were involved in this attempt.
Often, chemical reactions are speeded up by surfaces, as in the case when the gaseous molecules come in contact with a metal surface. Gerhard Ertl developed a number of methods for studying surface chemical reactions. He made use of techniques for producing very pure vacuum, which has been developed within the semiconductor industry. He was able to map out details of a process of great importance in the production of artificial fertilizer. The Hypovolcano process, in which nitrogen in the air is converted to ammonia via an iron catalysis, which I have also introduced to you in our another class about the Nobel Prize winner Fritz Haber. Beginning in the 1960s, Gerhard Ertl wanted to gain a complete picture of a surface reaction. He developed groundbreaking methods to searching surface chemistry. His methods are still applied today, not only in the academic research, but also in the development of processes for the chemical industry. He also laid the foundation for an understanding of car catalytic converters and fuel cells. He interpreted the mechanism of Hypovolcano process, which enables the production of artificial fertilizers from atmospheric nitrogen, and the process was developed by two other German chemists, Nobel Prize winner Fritz Haber and Carl Busch. However, it was Gerhard who first enables a complete understanding of the process, and as a result, its optimization. In 1986, Gerhard Ertl became director of the Department of Physical Chemistry at the Fritz Haber Institute of the Max Planck Society in Berlin. He helped focus the work of the famous institute on chemical reactions that are influenced by the structure of solid phases. The chemical reactions involved breaking of bonds between atoms and the forming of new ones. This process is associated with transformation of energy, and the energy diagram illustrates the process of reaction A plus B to C is illustrated in figure 1 here. An increase of the reaction probabilities can be achieved by either increasing the temperature or lowering the activation energy of the reaction. In the living systems, micromolecules, for example enzymes, play the role of catalysts. In the technical reaction, mostly the interactions of molecule with the surface of a solid is decisive. The principle of this heterogeneous catalysis is shown in figure 2 here. The atoms in the surface layers of solid have fewer neighbors than those in the bulky and are hence chemical unsaturated and may form new bonds with suitable molecules collided from adjacent gases or liquid phase. By this step, existing bond will be modified or maybe even be broken. The formed surface species may jump from one side to the near ones, then may react with others, and form the product molecules that eventually left the surface. How can the two-dimensional chemistry taking place in the chem-sorbed overlayer to be investigated down to the atomic scale? A possible strategy to overcome this problem has been suggested by Lamier already many years ago. Most finite divided catalysis must have structures of great complexity. In order to simplify our theoretical consideration of reactions at surfaces, let us confine our attention to reactions on plane surfaces. If the principles in this case are well understood, it should be then possible to extend the theory to the case of polar bodies. In general, we should look upon the surface as consisting of a checkerboard. Figure 9 shows different surface of concentrations of nitrogen atoms chem-sorbed on various iron single crystal surfaces with exposure to nitrogen gas. There is a pronounced influence of the surface structure. The most densely packed 110 surface is least active, while the open 111 plane exhibits the highest sticking coefficient and is indeed responsible for the overall activity of the industrial catalysis. All further steps involved in the ammonia synthesis reaction could be identified and analyzed similarly. So the overall mechanism and energy diagram reproduced in figure 10 here could be derived. This diagram exhibits the general features. Instead of overcoming the prohibitive high energy barrier for dissociation of the reaction molecules, the catalysis offers an alternative reaction path through formation of intermediate chem-sorption complexes. Those energy differences can be readily surmounted by the available thermal energy. What did Ertl say in Nobel Prize lecture? He said, "There's no review article about a brief account of a broader audience of some of the work which had been considered to be the basis for the award. Numerous co-workers were involved in our continuing attempt to understand how chemical reactions on solid phases take place. Without their efforts, the results pretended could not have been achieved, and therefore, I'm heartily grateful to all of them." That's the Nobel Prize winner for today's class. Thank you for listening.
大家好，2007年10月10日是德国科学家格哈德·埃特尔71岁的生日。当他正和妻子共进午餐庆祝生日时，一个电话打破了原本平静的氛围。他被告知获得了诺贝尔化学奖，这个消息让埃特尔喜悦之情无以言表。他称这是一辈子只有一次的生日。 埃特尔与中国交往比较密切。自1997年起，埃特尔教授就应聘为中国科学院大连化学物理研究所催化基础国家重点实验室国际顾问委员会委员，并同时应邀开始担任大连化物所催化学报的顾问。谈到埃特尔，几位科学家的评论如下：瑞典皇家科学院评审委员会说，格哈德·埃特尔成功地提供了详尽描述涉及化学反应如何在固体表面上发生，以此方式为现代表面化学奠定了基础。中科院大连化学物理研究所研究员李威雪说，格哈德·埃特尔对人非常谦和，他兴致好的时候还会邀请几位擅长小提琴和单簧管的朋友组成小乐队，一道为大家演奏几支曲子。北京大学化学与分子工程学院院长、长江学者特聘教授吴凯说，格哈德·埃特尔是一位了不起的科学家。好了，本次课到此结束，谢谢大家，再见。